Good morning, mathematicians out there. My name is Greg Wagner, and I was one of the senior markers for questions 11 and 16 of the Extension 2 paper this year. Welcome to this presentation. Starting off with question 11A, and this was a question on complex numbers. I know you have the question out there, but I will talk to it in a short way and then look at some of the little hints and tips around this particular question. So the two complex numbers, Z and W, were given to you, and the students were asked to find the product, ZW, and they had to give the answer in a particular form. There's the solution in front of us there. 2 quick lines for 2 marks. A little bit of information around this particular question, and I'll just read to this. The majority of students were easily able to find the correct solution, identifying the complex form required and adding the arguments when multiplying complex numbers. A number of students decided to convert their complex numbers into other forms before converting back to the required RE I theta form. Unfortunately, this approach usually led to errors and also was very time wasting. Advice to teachers around this particular topic area: make sure your students identify different complex forms, make sure they can apply index laws to multiply complex numbers using the Euler form, and the theory says add the arguments when multiplying complex numbers. Moving on to 11B. This question was given with particular notation: find sigma n equals 1 to 5 of I to the power of n. And the solution is detailed for us there. So the sigma notation suggests that we should have 5 terms, all powers of I, a little bit of simplifying, and then the final answer of I. This question had a few little issues around it because students, if they didn't understand the sigma notation, sometimes thought they only had to put n equals 1 in. Sometimes they thought they only had to put n equals 5 in. In both cases, they gave the answer I. So it's a suggestion here is to make sure students show all their working, and for 2 marks, students should know to do that. Now, in this question, the majority of students were easily able to find the correct solution, immediately writing down the integer powers of I and collecting terms. Surprisingly, for Extension 2, a number of students did not understand sigma notation. And advice: make sure students understand sigma notation, as it is part of the Extension 2 course. Also, show all working in 2-mark questions. For that reason I suggested before, the first term and the answer were the same, and only with working out can full marks be certain to be attained. Moving on, question 11C, and this question was asking students to find the angle between 2 vectors. And the question was well done by most students. They knew to apply a particular formula. The formula is written on the 4th line, and the working out comes just before that. So some information regarding this part question. The majority of students were able to find the correct solution using the standard reference sheet result. A surprising number of students made arithmetic errors in calculating the dot product and or the vector magnitude, in particular the dot product. The common mistake of 0 times 1 equals 1 surprisingly occurred in at least 5% of incorrect solutions. Other mistakes were made in the magnitude formulas of a similar degree of difficulty. So what sort of advice can you give around that? Well, definitely make sure students have used the formula cos theta equals the dot product divided by the product of the moduli in a variety of ways. I guess this sort of advice, take care with simple arithmetic when substituting into formula. Amazing number of students made that mistake of 0 times 1 equals 1, which affected their final answer. 11D, part 1, was a question which says, find the 2 square roots of minus I, giving the answers in a certain form. Now, this question could be done rather succinctly using geometry. Our solution here shows using algebra. But setting things up with the first line, the next 3 equations follow, leading to values of x and subsequent values for y. The students did have to put the answers in this form, x plus iy, for 4 marks. So some tips around this particular part. The question was approached in many ways. The best responses concisely found the 2 square roots of minus I using geometry or easy algebra. Less efficient solutions were given by many students dealing with complex equations like z squared equals minus I with much algebraic difficulty. Adding to that, many students chose drawn-out methods involving algebra. Further mistakes occurred commonly with negative signs. Those methods typically went over 2 pages, and you can see from the solution that it could have been done concisely with a few lines. Advice: make sure your students understand the geometry of complex numbers to quickly access problems. Very few typically showed this understanding. And make sure the students have a variety of methods for finding square roots and do not apply a rehearsed approach to all questions. Okay, moving on, but related to part 1, part 2, hence or otherwise solve that particular quadratic equation, giving your solutions in a certain form. Now, most students picked up very quickly that they had to use part 1 in some form in part 2. And our solution here uses the quadratic formula to give the 2 values of z, and using part 1, substituting in, gave them the final 2 answers to the question. This question intended for students to join the dots between question marks and was well done by the majority of candidates. Again, methods tended to be drawn out, but most students handled the question well. Common problems. Some students did not observe that the question asked for the solution of a quadratic equation, nor did they connect parts 1 and 2. Those students who completed the square saved time and avoided areas where mistakes might have occurred. Advice to teachers: make sure students are able to apply a range of efficient strategies when solving quadratic equations. Make sure students are aware that parts 1 and 2 are connected, and the use of hence in the question needs to be understood and observed. Now, part E, the complex numbers Z and W were given. Students had to find conjugate of Z divided by W and give their answer in Cartesian form. That meant that they needed to know what Cartesian form was. Okay. This question was handled very well in general, with some errors occurring typically in arithmetic and algebra. Common problems, well, very little to comment about in this question as it was very accessible to students. Advice to teachers: make sure students are careful working with I squared equals -1 and algebraic terms. Okay. The last question in question 11, 11F, asks students to express that particular fraction as a sum of partial fractions. Sorry, I was delayed somewhat just then. Now, the solution for 3 marks required students to set the division in a particular form. Then applying an identity and using a range of methods to find the values of A, B, and C. This question, even though it was hard, was done very well, with most students readily finding the correct partial fractions. Better solutions used a combination of techniques involving identities, in particular substituting appropriate values. Issues were not understanding the correct form for irreducible quadratic factors in the denominator. Mistakes were made solving simultaneous equations with 3 variables. And a small percentage of students thought the question needed integration techniques applied beyond the partial fractions, clearly not distinguishing between topics. This was typically very wasting of time. Advice: make sure your students understand partial fractions across a range of types, and in particular those with irreducible quadratic factors. And realize that substitution into an identity is a very powerful tool for partial fractions. So this was the breakdown for question 11. It was complex numbers very much addressed, as you can see. A little bit of vectors and a little bit of calculus at the end. Okay, no more comments about question 11 from me. Moving on to question 16. And this was the last question on the paper, and one that was very challenging for students. Now, 16 part A had 3 parts to it. In part 1, and I'll just read to this: the point B, X, Y, and Z lies on a sphere of radius 1 centered at the origin, and using the position vector that was given to the students and the triangle inequality, students had to show that particular result, which is, if you like, a lower bound for that particular sum. So the solution is given there to us, and it played out quite nicely. However, for students, there were a number of issues, as you probably would expect. The topic of vectors is a new one. Students aren't so comfortable with it. Their use of language, the use of notation, was suspect. And this is what I have to add to that. Question 16A had 3 parts and proved to be very challenging. In essence, the question was asking students to find the lower and upper bounds of the sum of the 3 moduli when the point X, Y, Z sat on a sphere of radius 1, centered at the origin. In part 1, better responses saw students apply the triangle inequality as an identity and use it to show the lower bound for the expression is 1. Now, common problems occurring here were this particular one. Many students did not understand the difference between the magnitude of xi vector plus yj vector plus zk vector and the magnitude of x plus y plus z. Now, given that bold use of letters also constitutes vectors, it was hard to know if students knew the difference. And the second error here was that the triangle inequality wasn't particularly well understood, and use of it was very problematic. Advice to teachers: well, make sure students use vector notation in a precise manner. Make sure students are able to operate with the magnitude of a vector using appropriate notation, and make sure they utilize appropriate formula and identities in the vectors topic. Okay, moving on. Part 2. This general question around vectors in 3D asks students, if they were given those two vectors, show that particular inequality. On first sight, it looks rather complicated. Most students who did this question well were able to realize that the standard reference sheet result around cos theta could be applied. They saw the dot product perhaps on the left, they saw the product of magnitudes on the right, and then they related it back to a known formula. There was still work to be done after that because the inequality had to be taken care of, and that proved to be a little bit of an issue for students. That inequality came about if students realized the absolute value of cos theta needed to be less than or equal to 1. Now, better responses identified a correct relationship, typically that one that I just spoke to. This then led to a correct inequality involving the dot product and the product of the magnitudes upon consideration of cos theta. In this question, many students were not clear with their intent. It was a show question, but they did not really understand what they were trying to show. Inequality symbols were regularly misapplied, and some students thought part 1 assisted with part 2, drawing incorrect conclusions around this general inequality. Advice: well, make sure students understand dot products and their notation. Make sure students correctly use absolute value or modulus symbols across vectors and scalars. Now, part 3 of this question 16A asks students to combine parts 1 and 2. And the question says, as in part 1, the point lies on the sphere, centered at the origin, and using part 2, show that the sum of the magnitudes is less than or equal to √3. So an upper bound, if you like. Those students who did this well needed to make the connection between part 2 and part 3. And that meant coming up with a particular vector A and a particular vector B as detailed in the solution. Most students struggled to identify the correct vectors A and B. So, some information regarding this part. Very few candidates were able to give a correct solution to this part. Most students were clearly attempting to link this to part 2 without really understanding the nuance in the question around the upper boundary. Better responses saw students carefully choose vectors to apply in a part 2, thus leading rather quickly, in fact, to the required upper bound of √3. Common problems. Again, most students did not observe the intent behind this multi-part question. Results tended to be fudged, and part 2 was not correctly applied. So advice here, well, make sure students understand inequalities using vectors, and make sure they seek to find the intent behind multi-part questions. Not so easy to do when it's late in an exam and you're trying to connect the dots in a very difficult question. But if students can aim to see the intent, it will make a difference. Now, 16 part B was the very next question, a question regarding projectile motion. This was a lovely question, and I'll just read a little bit to it. A particle projected from the origin with an initial speed at an angle theta lands on the x-axis, and there's some conditions around that particle, gravity. The position vector, was given to students. Okay, and you can see that below. And the question had two parts to it. For some values of theta, there will be 2 times during the time of flight when the position vector and the velocity vector are perpendicular. Students had to find these values of theta, find these angles, and justify that both times occur during the time of flight. Very detailed question, very challenging. I won't go through the solution there. It is fairly straightforward in as much as students were able to do it pretty much all the way down to the bottom. And that meant that they were able to identify the velocity vectors, the velocity vector from the given position vector. They were able to set the dot product equal to 0, and they were able to multiply out. Most students were able to do this, which was nice to see. Beyond that, there was difficulty. And the difficulty was shown in where students on this slide, you'll see the discriminant needed to be used, or an equivalent approach, to identify the particular angles. Interesting enough, the angle is more than 70 degrees, 70.52 degrees or higher, bounded by 90 degrees. So particular angles giving this particular result. That was only part of the question. The second part of the question did require students to justify that the times were within the time of flight. That required students to know the time of flight, and then some very detailed work needed to be shown to justify that there were 2 times and that they occurred during the time of flight. That meant the smallest value of time needed to be greater than 0, and the greatest value of time needed to be less than the time of flight. Talking to this particular question, well, this was a 5-mark question and proved to be very challenging. Without scaffolding, it required students to explore a number of related concepts in order to access the multiple parts in the question. Projectile motion, dot products, discriminant theory, and subtle arguments around time values or perpendicular vectors combined to create what I believe was a very good extension 2 question. In better responses, students correctly linked the ideas above to find a range of angles. Further work was required for full marks as they needed to justify their answers. And only approximately 10 candidates were able to give a complete solution for this question. That speaks to the difficulty of the 5-mark question. Issues? Almost all students were able to start this question setting the dot product of the position and velocity vectors to 0. However, unfortunately, algebra proved a major stumbling block in arriving at the correct quadratic equation in T. Many students found sine theta in terms of T, not realizing that they sought a definite range of values for sine theta and then subsequent values of theta. And the correct solution required students to answer the second part of the unscaffolded question. And most students either fudged this or were time poor and skipped over the necessary justification. Some advice. Well, for students, realizing the importance of discriminant theory in relation to quadratics. This comes up time and time again with projectile motion. Make sure students again take care with algebra and negative signs. And make sure students take note of the full question when it is divided into two parts, but not scaffolded. And to the last question, question 16C, the daunting last question on the extension 2 paper. And probably one of the most succinct questions that we've come across as a 16C, or as the last question. So the question reads, sketch the region of the complex plane defined by the real part of Z is greater than or equal to the argument of Z. Under the condition that argument Z had to be the principal argument. So this question had a fair bit to it, even though it was only very, very brief in its description. Students needed to introduce X's and Y's, in other words, a Cartesian approach to try and eke out a function. The function of importance here was y equals x tan x. It became the boundary for the curve, or the boundary for the region, I should say. Further consideration of quadrants needed to take place to gain the solution at the bottom of our page. Some comments regarding this question. I've written here that the question was a short, concise question, which proved to be very difficult for students. Showing the correct region in the Argand plane proved elusive, with less than 0.5% of students achieving a correct solution. Better responses came from students who found a Cartesian functional relationship, y equals x tan x, it needed to be, and used it to guide them to the correct region satisfying the required relationship in Z. Common problems, well, lack of knowledge of the connection between real Z and argument Z caused issues for the students. Not understanding that they could use Cartesian form X's and Y's also caused them problems getting started. And beyond that, poor use of quadrants. Advice, make sure students are able to make geometric and algebraic connections across complex numbers, and know appropriate Cartesian form when dealing with graphs involving complex numbers. So this last question only covered 3 topics. There was 15 marks, 7 of them around vectors, 5 around mechanics, and 3 around complex numbers. Okay, thank you very much. I hope you enjoyed the show.